welcome to this course module on paleoclimate. As a part of this module, we will learn what is paleoclimate, why we need to understand paleoclimate, how we do paleoclimate, and in the last fourth module, I'll show you a few examples of what we can learn from the paleoclimate, especially from the Indian Ocean region. Now, for those who have not heard the term paleoclimate, let's start with something very common that we know of. Let's look at the Earth first. This is something that we all are aware of. Our own very planet, Earth, looks blue, looks at parts green because of the lot of water that we have on Earth. Almost 70% of the Earth is covered by water. The unique thing about this planet is that it's very dynamic. It's not static. Things keep on changing. And then when we look at our surroundings, the way it changes, we see the climatic changes. Although there are other things that change, but the most severe thing that we see around us at any place, especially in India, changes because of the climate. And if we recall that one of the UN Secretary General, Ban Ki-moon, he has said that the climate change is the defining challenge of our age. That means we are the most affected by the climate change. And the way we see it on our surroundings near us is in the form of something like this. Especially in India, there are parts wherein we don't get any rain almost for years together. So we face drought. And at the same time, there are places which get flooded. A recent example is the severe flooding in Kerala. There were a lot of people who were displaced, devastated, and a lot of people died as well. Now, these are natural calamities. Unfortunately, we still don't have any means and ways to stop these calamities. We cannot bring rain, and if there is a lot of rain, then we cannot stop rain. So what's the way out? The way out is if we know about these climatic changes beforehand. If we knew that there is going to be a lot of rain in Kerala almost a year in advance, then we could have been prepared very well to face this calamity. That is why people try a lot to understand what is going to happen in future in terms of the climate change. The floods and droughts are not the only two things that affect us. We can think that, okay, if I'm living in a house, then the flood is not going to affect me much. Or if it is not pouring, I do have some pump of some means and ways to get the water, that is also not going to affect me. But then that's not the only aspect of the climate change. It seems the climate change is affecting almost all these spheres of our life. Look at some of these papers that I have taken few titles like the climate change and the global malaria recession. I hope all of you know about malaria. It's a very deadly disease which happens by if you are bitten by a mosquito. So there seems to be a link between climate change and the spread of this disease. Not only that, the food grains, we eat chapatis that is made up of wheat or even rice. That food grain production is severely affected by the climate change. The extreme events, like the one I gave you an example about, like the Kerala flood, they seems to be increasing because of this climate change. That means that climate change is affecting almost all these spheres of our life, and we need to be better prepared for that. And as I said before, that if we want to be better prepared for that, the way out is the climate prediction. See, the way we look at the climate change, we see that most of the people are talking about that human-induced climate change or anthropogenic climate change. Why do we say anthropogenic climate change? Because we see a tremendous increase in the greenhouse gas concentration in the atmosphere, especially carbon dioxide, since the Industrial Revolution. Here is a graph which shows you how the carbon dioxide in the atmosphere have changed during the last 800,000 years. This graph has been developed based on the ice cores drilled in Antarctica. So we know the atmospheric composition of carbon dioxide concentration going back to 800,000 years. Now, if you look at the graph, the carbon dioxide has changed between 280 ppmv and down to almost 150 or 120, 180 ppmv during the last roughly around 800,000 years prior to Industrial Revolution. Now, after the Industrial Revolution, if you come back to this point over here, as you can see down, we have increased the carbon dioxide concentration in the atmosphere by almost same amount that used to change naturally in the last 150 years. That's the reason that we feel that we are the reason or we are the cause behind the climate change impacts that we see today. Now, because we know how much the population will be in next 50 or 100 years, we also knew how the vehicle usage is going to change in the next 50 or 100 years. So we know what will be the atmospheric composition of the greenhouse gases. Accordingly, we can predict what will happen in the future. There are a lot of people who are trying to understand what is going to happen in future. And there is a consortia of the people involved in climate change research, all aspects of the climate change research, whether it is physical basis, the biological aspects, the biogeochemical aspects, the societal aspects. The United Nations has formed an umbrella organization that's called Intergovernmental Panel on Climate Change. They meet routinely and they come up with consolidated reports. Now, what they say, since the concentration of greenhouse gases is going to increase, we will see an increase in temperature. And the increase in temperature will be such that in the next, you can see the year on the x-axis, starting from year 2000, then 250, and then going to almost 2100 years. Now, the way temperature is going to increase, it's shown in this line over here. If you start from a point now, then it is predicted that the temperature is going to increase by almost 3 to 4 degrees centigrade in next 100 years, or rather now almost 80 years. Now, since the temperature is going to increase, it will not be the only change, because Earth, as I said, is a closed system and a dynamic system. If we are going to get warmer, things are going to get warmer, it will increase the sea level. So it's also predicted that the sea level is going to increase by almost on a higher side by meter, or 0.8 to 0.9 meters. Now, as I said, that we say about these aspects of the climate change because we know that the greenhouse gas concentration is going to increase. Now, when we say about these climate prediction, there are few things that this is entirely based on the premise or understanding that the greenhouse gases are the sole reason behind the climate change. Now, if we look at the way things change, the monsoon. In India, the monsoon is one of the most important phenomena. We know that India is an agriculture-based economy. Things are relying heavily on the monsoon. The monsoon records for the last almost 130, 140, 50 years is shown over here, starting from 1870 almost till year 2000. The important aspect or interesting aspect of this monsoon record is that we do see a multi-decadal variability. If you look at the graph over here, it increases and decreases on a periodicity of 60 years. So we do not see any linear increase or decrease in the time interval for which we have the available recorded data, any linear change. Now, if the greenhouse gases are linked with almost all the change on the earth, then we should see a linear change, but that is not happening in case of monsoon. At the same time, the temperature in the oceans is also not increasing linearly. Like if you look at the overall temperature, we do see an increase, then almost a flat, and then again an increasing trend. Now, these changes in the monsoon as well as the temperature in the oceans, which are not directly linear or not linked to the greenhouse gas concentration, suggest that there is an added component, most likely of the internal variability of the climate, which also has to be looked at. Now, there are few aspects as far as the climate prediction is concerned. One is that there is an internal climatic variability other than, or rather natural climatic variability other than the greenhouse gas concentration, and then the validity or the robustness of the predictions. Now, let's look at how the climate prediction is done. Now, assume a person, a climate modeler, sitting on a PC and then trying to understand the climate change. What they do is that they try to simulate, look at the interrelationship between various parameters. For example, how much sunlight we get from the sun, how the greenhouse gas concentration change, how the sea surface temperature changes, how the thermoline circulation affects the other parameters. So they try to understand the relationship between these different parameters, and then they run it for the future wherein we know the greenhouse gas concentration, and they suggest or come up with some estimates that the rainfall and temperature is set to go up in India. Now, what is the validity or reliability of these predictions? That has to be tested. In order to test that, what we can do is we can ask them to simulate the climate change which we have already seen, for which the records are available. Unfortunately, if you look at the recorded climatic variability, that is quite limited, and it is nowhere what these climate modelers predict. That means either there is some problem with the climate models, or there has not been a large climatic change in the last 100-150 years. But what about the geological past? Earth has been there for a very long time, in fact, for almost 4.6 billion years. So, are there any other time intervals wherein there was large climatic variability like the way the climate modelers are predicting? For that, we have to go back in time and then look at the geological past. But again, the problem arises that there are no written records. So, we have to rely on indirect techniques called proxies. Now, how do we go back in time and understand the climate? That is what is the paleoclimate, climate of the past. And I told you the reasons why we need to understand the climate of the past. Now, I will briefly tell you how do we reconstruct the climate of the past. To put things into a better perspective, I hope all of you are interested in understanding what is going to happen in future. Almost a few of you might also look at the daily horoscopes that are being given in the newspapers. Now, if somebody comes to you and he says that he is astrologer or jyotsi or what, and then he can tell you about your future. Whatever he tells you about your future, are you going to believe him? Is there a way to cross check whatever he or she is telling about your future is correct or not? There is a way out. You know you have lived your life. If you are, say, 18, 20 years old, you know there are some important events or incidents happened in your life. You might have fallen sick, you might have met with an accident or any important event. Now you can ask that astrologer or jyotisi, okay, tell me about my past. If he or she correctly tells you about your past, then there is some likeliness that he or she, whatever is telling about your future, it may happen. Now that's something like the job of the paleoclimatologist. The climate modelers talk about the future. Paleoclimatologists ask them to test their models by providing them the data about the past, about the events which have already happened. Now, how the paleoclimatologists do that, let's look at that. The principle of, or the basic principle of the paleoclimatology. Now, just look at this picture and what comes to your mind. By looking at it, one can think of, okay, these guys have got fairly dark complexion, their hairs are unique, and they are most likely from places in Africa. We know that they have got this peculiar facial features and the hairs because the temperature is quite high in Africa. So we can relate the complexion with temperature, although there is nowhere mentioned in this picture that the temperature is higher or lower. Now, contrary to that, look at another picture. While looking at it, definitely we can say that these people belong to a cold climate. So here there is no climate data, the temperature data. But still, since there is some background data in our mind that the warmer temperature leads to darker complexion and the cooler temperature leads to fair complexion. So we can relate. Just by looking at them, we can find out the climate of the place where they belong. This is what in nutshell is paleoclimatology. We try to look at present, try to establish the relationship between climate parameters and the things that we see, and then go back in time. Now let's imagine if these people are buried at some place and then whether we can reconstruct paleoclimate from them. So I'll just give you an example. Here is a place. Modern conditions are warm, as you can see, with the people being of very dark complexion, like here and here. Now imagine that somebody is digging up a well over there in a lake and then it's going back in time. We know that the sediments get deposited over a long period of time. So probably the layers at the bottom are the oldest, and the way we move up, the layers are getting younger and younger. Just assume, although I know that this does not happen, but just try to assume that these people are buried. Somehow the tradition at that place is that they bury their people. And then we start going back in time, we are finding those people buried nicely over there. I'll again repeat that in practice or actually it does not happen, it's just an example. Now you started digging back and we are going back in time. We start getting those nicely buried people. up to this layer that I have shown you and these people we have recovered, what we can understand is that the climate was warm like the way it is today. Now, if you go a little further down and then we see some fair complexion people, then again going back in time, we do see some dark complexion, again some fair complexion, and again some dark complexion. So we are going back in time and unearthing the people who are buried over there. Now there are a few peculiar things. Although the present day climate is quite warm over there, but at some point of time, you do see a fair complexion people buried over there if they were living over there. Now the question arises that what is the significance of these fair complexion people being buried over there? There can be several implications. It's possible that these people visited this place like it happens, say especially in tourist places like Goa, where a lot of people visit, and unfortunately if something happened and they get buried, that may happen over here as well. So they are not the representative of that place. But if you can rule out that possibility that no, these people lived over there, and then we rule out the possibility of transport, then another thing that we have to look for. In longer time scales in geology, the landmass move from one place to another place. The place where we live today in India, that was way down close to where Antarctica is today. So we can imagine that we have moved all the way from Antarctica to almost the latitudes that we are today. So if you can rule out both of these possibilities, then what remains is that this change that we are seeing is basically because of the climate. So when these fair complexion people were buried, probably that was the time that the climate was quite cool over there. Now that's the basic premise or principle of the paleoclimatology. We establish the relationship by looking in modern times and then we go back in time. Unfortunately, the way I showed you the human beings, they don't get buried so well. The skin goes off very quickly. So remains are not seen over there. So we have to look for other means and ways or other methods or proxies. Now, in order to understand the relationship between the modern parameters and the proxy, we use several techniques. One of them is like field studies, and then we can also develop those proxies by culturing some of the organisms in the laboratory. Now, the way we develop the proxies from the field is just an example of the Indian Ocean, Northern Indian Ocean. You can see it's a temperature profile of the Northern Indian Ocean. And imagine that we are going from the northern point in the Arabian Sea down south, and similarly we are going down in the Bay of Bengal from the northern point to the point almost in the south. So what we have done is that we have taken a ship and then taken samples at regular intervals. We collect, say, water or the sediment samples at the same location. Now, once we come back to our lab, we can do a lot of parameters on that. And first, I'll show you how do we collect these samples. We can collect the sediment samples by using a grab sampler or by using a spade core, or another modern method of collecting these samples is the multi-corer. Multi-corer is something like this, which gives you the samples from the surface and you get even the water column quite intact when you collect samples by using a multi-corer. So that's the methods to collect the surface sediment samples. And we also have the water samples. Now what we do that the water can also be collected by using a CTD as well as the multi-plankton nets or simply a plankton net. So what we do, we bring the sediments into lab, we process them and take out some species out of that. So any individual. Here I'm giving you an example of a typical organism which is quite common in the oceans, Foraminifera. And we count its number and then make it uniform in all the samples, number per gram sediment. And at each of those stations, we have noted down the surface seawater parameters or even bottom seawater parameters. Now what we do, we try to establish some relationship, what are the factors which are affecting the abundance. So here we have correlated that with the water depth. So you can see that the way these abundance of these organisms is changing with the water depth, it doesn't show a very peculiar trend. It's spread all over. We don't see any clear trend. So let's try to correlate that with another parameter like say salinity. At least here we see some trend that the most of the samples are falling on this line. But then there are other samples which are falling out of the line. So let's look at some other parameters. Say for example, the seawater temperature, and here it shows a relatively better trend. But then there are again few samples which are out of this trend line. So we need to really find out what is the reason that these few samples are out of the line and most of them are following on a line. But then with this technique, we can find out that the seawater salinity and temperature seems to influence the abundance of these organisms. So we have a proxy now or a technique to go back in time, that if we see any change in the abundance of these organisms, which is listed over here as G. ruber, then we can talk about the changes in seawater temperature or salinity. Just to tell you briefly some of the examples or the techniques that we developed from the Indian Ocean. The Northern Indian Ocean is also known as the low oxygen minimum zone. What we did, we tried to understand or develop a proxy to reconstruct the changes in the oxygen concentration in the seawater in the past. So samples were collected along some transects in the Arabian Sea, in the Eastern Arabian Sea. And then from these samples, we took out the foraminifera, a particular type of foraminifera. They are serial forms, as you can see. These chambers are arranged in a line, all those serial forms. So the abundance of these serial forms was calculated and then plotted as per the water depth. Now you can see there are two peculiar peaks in the abundance of the rectilinear forms. One in the shallow water and another from around 120 meters to going to almost 1200 meter water depth. Now these two zones are the regions wherein the dissolved oxygen is very low. That means we can reconstruct past low oxygen intensity zones by looking at the abundance of these species which we have listed as the rectilinear benthic foraminifera. Their abundance increases whenever the oxygen concentration goes down, and their abundance decreases whenever the oxygen concentration goes high. Similarly, there were few proxies that we tried to refine or develop based on the laboratory culture experiments. Here is an example that we took out a small organism, subjected that to different salinity. As you can see, the salinity is 10, 15, 20, like that, up to 40. What was peculiar was that at salinity below 20, the organism starts dissolving its hard part. These organisms have a hard outer skeleton like the way have bone. They have a outer hard part that is called a test, and that starts dissolving below 15 per mil salinity. And then the growth is also affected by salinity. So we have a proxy to understand the past salinity changes. Similarly, the temperature also affects them. We can see that the peak temperature is somewhere where you find the maximum reproduction that will affect the abundance. That means abundance can give you an idea about the temperature. Here is another example how the organisms are affected by the ocean acidification or the pH. So we have a proxy for pH that if you decrease the pH below certain points, the organism starts dissolving. The growth is negative. At other places, the growth is either flat or positive. Now, these are the way that we do the paleoclimate, and I told you about the reason why you need to understand the paleoclimate. In the next module, I'm going to talk about a little detail about the proxies or the techniques that are used to understand the past climate.